Good morning. How are you guys? Everybody can see me? Everybody can hear me okay? Wonderful. I'm so excited to be here. As Mike said, my name is Brainstorm Bill, and I am a mad scientist. Now, I don't mean a mad scientist like the lady with the purple hair in the Paw Patrol movie. All right, not that one. I'm not a mad scientist like that. I am a mad scientist because I am just really excited about science. I love it. I think it's really cool, and I have a lot of cool stuff to share with you. I even have a game that we could play. Would you like to play a game? Should we play a game? I like games because it's a great way of getting to know people. And this game in particular is really important for science because it's a listening game. Now, who can tell me why they think it's called a listening game? Any ideas? Yes? Because you have to listen. Very good. Excellent. So this is simple. Have you ever played Simon Says? Yeah, this is even easier than Simon Says because I'm not even going to say Simon Says. I'm just going to bark things out and see if you can follow them, okay? For example, I might say, hands in the air. Oh, you guys are good. Hands to your head. Hands in the air. Shoulders. One finger in the air. And we go, shh. You guys are really good. I am impressed. Let's see if you can do it a little faster. Okay, you ready? Hands in your head, hands in the air, hands in your shoulders. Ah, I got you. Sniff your armpit. Don't do that, that's disgusting. What's wrong with you? All right, so one more quick thing before we get going. I have 3 real simple rules we all need to follow so everybody can stay safe and have fun and a good time. Rule number 1 is I have just myself and Spectrum Sammy here, and there's a lot of you. So if you have something to share, if you have a question, if you have an answer to a question I ask you, please just raise your hand. Please no talking when I'm talking because that way everybody can hear. And also no talking when some of you are talking with me or with Sam. Rule number 2. Yes, thank you. Math wasn't my strong point. You might be surprised. Science is awesome, though. Rule number 2 is, I got a lot of cool stuff here I want to show you, but please don't touch my stuff. Some of it could be, well, let me ask you, why do you think we shouldn't touch it? Yeah?
You don't know what it is, and it might be potentially dangerous.
It might be potentially dangerous. That is the best answer I've ever heard. Yeah, usually I get somebody saying, like, maybe it blows up.
What?
Yeah? And I think that is a really rude question because I haven't blown anyone up all week. And it's already Saturday, so I just need to make it through today, and I'm good. Yeah. Last rule is very serious. It is the most important rule in all of science. And that rule is have fun. I heard somebody say it. Somebody's an expert already. Yes, have fun, because science is about discovery, and it's exciting, and it's cool, and it's a way we can discover ways to predict how things are going to happen in the future. That is very handy. And practically everything that we enjoy in our lives today exists because somebody did science. Now, when we were playing that listening game, I said this was important for science too. And that is because listening is a form of observation. Some of you might be thinking, hey, I'm just a kid. I don't know what observation means. I don't know if that was Stitch or Smeagol. It might be a mix of both, but I was going for Stitch. Can anyone tell me what they think observation means? Yes? I'm sorry, say that one more time.
Basically, you're just
Looking at the person? Yeah, looking is one type of observation. You've already did another, which is listening. Yes?
looking at what someone is doing and doing something like that.
That is a great example of it. Yes, observation simply means anything we can learn by using our 5 senses. You can touch it, you can see it, you can hear it, you can smell it, you can taste it, right? Today we are not going to be tasting the science. Actually, maybe we can later on afterwards. I have one kind of science. Actually, Samantha's got one kind of science you can taste if you want. But we'll get to that later. So, are we ready to have fun?
Yeah.
Are we ready to see some magic?
Yeah.
Too bad, I don't do magic. This says mad science, not mad magic. I can't do magic. Well, you know what? There is.
Science is basically magic.
I thought I heard something, but I didn't see any hand. Oh, yes.
Science is like
I like that answer, and that's really good. It sometimes is the way magic works. When you see a magician, what do you call the things that magician does? I think I heard an answer, yes? Magic wands, they use them to perform magic. Yes? Tricks. You know why they're called tricks? They're tricking you. Most magic is based on deception. They're getting you to look over here at something flashy while they're secretly doing something else, and they found your card, right? Or they are, like you said, using science, but they're not saying it's science, they're saying it's magic. But like I said, I did have one magic trick I was practicing, so I guess I'll share it with you if you'd like. But I'm not, every time somebody pulls out a deck of cards, somebody, I've seen this before. There are literally thousands of card tricks out there. So maybe you've seen this one. Oh, you have cards, that's great. Maybe you have seen this one before, but if so, well, you know, the polite thing to do is not spoil it for anybody, right? But I might need some, you already know what I'm gonna ask. Well, here's the thing. One way I pick a volunteer is I'm also looking for somebody who's following those rules really well. And I saw this young lady with her hand up very nicely. Why don't you come up here? What's your name? Sana? It's lovely to meet you, Sana. All right, so have you seen anybody ever do a card trick? No? Okay. Well, there's usually something that has to be done at the beginning of any card trick, right? We gotta shuffle cards. So that's kind of boring to watch. So Sana here is gonna do a dance for you. Well, go ahead. I'm kidding, you don't have to dance. Obviously you're not a dancer, you're more of a singer. Okay, go ahead, let's hear it. No? It's okay, I'm just teasing you. You don't have to sing, you don't have to dance. What you do have to do is pick a card. Oh, wait. Make sure I don't see it, okay? So wait, I'm gonna close my eyes and then you can pick a card, okay? You ready? Well, obviously you also need to see it, but they all have to see it, right? So when you pick the card, I'm gonna just cover my eyes and you're gonna show everybody the card, okay? So everybody can hear the card, see what the card is. All right, here we go. One more thing. All you guys in the audience, you gotta be cool, all right? You can't be saying, oh wow, what a beautiful queen. That's my wife, that's not the card. And even if it is the card, now I'm gonna know what it is and it spoils the joke, okay? So you gotta be quiet. Okay, nobody tell me what the card is. All right, here you go, pick a card. You got one? All right, don't show me. All right, show the people over there. Show all the people over here. Yeah, show the people in the ceiling. All right, we all good? Okay, go ahead, put that card in my hand. Come on, this isn't Marco Polo. Oh yeah, all right, great. Okay, all right, just to make sure everybody saw, there's the card. Make sure you don't tell me what it is, because if you told me what it is and I saw that it was the Nine of Hearts, I told you I wasn't really good at magic. You know what? How about this? Maybe I should just turn this into a science demonstration. How about that? Do you think we could change this card?
Rip it.
Change the card? You want to change this card for me? Why don't you take a hold of that? Fold it in half. Go ahead, fold it in half. Yep, there you go. Beautiful, beautiful, beautiful. Okay. Now, does that card look different? No.
Maybe.
Does anyone think it looks different at all from the way it was before? Yeah. It looks like it's mail now. Okay, it looks different. Yeah. Looks like full paper. Okay, it's still paper, right. Maybe we should change it some more. Go ahead and tear that card in half.
Yeah.
You can tear it right where you folded it. It might be easier.
Yeah.
This way.
Open it and then rip it.
There you go. Yeah, okay, is that card changed?
And you're going to put it in the bucket and then you're going to put fire out.
Okay, do you need to sit with mom and dad? Okay, then don't spoil this for anybody. Okay. What we just saw here was an example of a physical change. Everybody say physical change. Nice, nice. That's a physical change. That means you're changing an object's shape, its appearance, but you're not changing what's it made of, right? So, I guess now what we have to do is observe. Sana, what is this card made of? Paper. Paper, probably some plastic. It's very shiny and slick. But yeah, it's mostly made of paper, and it's still made of paper. So I guess I'm going to have to do something else to change that. Maybe I will have to use fire. Sana, you can sit down. You can sit down now. Thank you very much, Sana. Everybody give Sana a round of applause. Thank you so much. All right. So yeah, a physical change, we do them all the time, but it's not that big of a deal. We're changing how something looks, shapes, something like that. I gotta get this thing going here. This here is what's called a chemical change. And these cards are a little stubborn here today. Boy. I'd say that's pretty good. I think I need a drum roll here. Oh, there we go. There we go. All right. I better put that out. Oh my God. Did I tell you or did I not tell you? I'm not a great magician. Oh, that's great. Well, obviously we did have that paper go through a chemical change. Yes, it burned. And yes, the idea was that this was hiding in there. And guess what? That's another way scientists are different from magicians. A magician never, ever tells you how a trick works, ever. Scientists will always, always tell you how the trick worked. So we know paper burns. Why did we know that paper was burning? Can anybody give me something they observed that told you that paper was burning? Yes, young lady right here. Go ahead. Because you saw it was fire, right? You saw the flames. Yes, that's a sign of fire. Yes.
The flame caused the card to heat up and it burned.
There was a word in there. There was a word in there that was very important. He said heat. Yes, to have a fire, we're going to see flame, and we need a source of heat. And heat is also something that tells us something's burning. Yes.
Paper is made from trees, and trees have wood in it, and wood burns just like if you're like starting a campfire, and if you're using paper that's more made from wood, then it would definitely burn.
It definitely burns, yes, because it's flammable. You are actually a step ahead of me. You're talking about what fires need to survive, but when you burn something, do you have something to add, son?
When there's a real fire,
Yeah.
in a house, you need to call the fire.
That's also very important. You need to call the fire department. And I guess I should mention something. We all know what this is, right? So lighter, barbecue lighter, right? When we see these at home, do we touch them? When you see these anywhere, do we touch them? No, that's right. That's right. Because when children play with fire, and I knocked off my lapel when that little trick happened, or didn't happen. There we go. Yes, because when children play with fire, well, sometimes they get burned. Now, something might be missing from that. What do you normally see if you have it, like maybe you have a campfire, you have a fire pit in the backyard maybe. What's left the next morning? What do you see on the ground? Yes? You see ashes. Were there any ashes from that? There were not. You want to see it again? All right, here we go. So this is something that you might hear called flash paper. It is technically nitrocellulose. Now, the young man over there earlier said that the card burned because it's made of paper and paper's made of wood. That was all excellent. Cellulose is, it's made from trees. It comes from wood. Nitrocellulose, however, is a little different. It's got something extra in it. And it does something called sublimation. Can everybody say sublimation? Sublimation. There are 3 states of matter. You've got solids, liquids, and gases, right? Right now, you guys are all sitting close together. You are a solid. If I told you all to suddenly jump up and start dancing, would you take up more room on the floor? You don't think so? Maybe you're a really calm dancer? Would most people be taking up more room? Yeah. If I said, okay, everybody, we're going to go outside and run around like crazy, how much space would you take up? A lot of space. When you're sitting here on the floor right now, you're like a solid. If you were all dancing and moving around, you'd need more space between you so you're not bonking into each other. That's like a liquid. And when you're running around outside, that is like a gas. And gas takes up more space than solids or liquids. I want to introduce you to a friend of mine. This is Egbert. This is my friend, Egbert. He's my friend, he's my comrade, my colleague, my muse. And I like him so much that I got him a special home. Oh, we all know what this is. You see this thing, and you know science is happening, right? This is called an Erlenmeyer flask. Erlenmeyer flask. We like naming things after people. There's just one problem. Egbert is a little bit like me. He eats too much, and he can't even fit in his home. I can't get him in there. Now, does anybody want to form a hypothesis, a smart guess as to how I might get Egbert in there? Yeah. What do you think? Not sure? Yes?
Get the lighter.
Uh-huh.
And light inside of it and make it hot and like put him in and then you go in.
Okay, he thinks if I burn something in there, I can get him in there. Yes, on the end.
I think that you should like keep the paper in there.
Uh-huh.
And then you should like keep more paper in there and then light the paper. And then when the paper's light, then you keep it inside and then it'll slowly start going.
Okay. I think this guy has a good idea. I think we should give that a shot. So, the idea is that if we make fire in there, maybe Egbert will decide to come in. Maybe he just wants some nice, cozy place to live here. Yeah, he's not really wanting to go. But oh, wait. No, he doesn't want to go.
No, like the thing is that when the paper is on fire.
Uh-huh. You think we need more fire?
Yeah.
The solution to our problem is more fire?
Yeah.
I am concerned about you guys.
I heard this is all about fire.
Oh, you are making a great hypothesis. You are using what you know about the show to decide. Yeah, there's too much smoke in there. 1 second, I have to do something else. I'm actually going to be introducing you to another principle of physics. That's called Bernoulli's principle. You'll get to see a little bit of that later. But the principle of what? Not really. I'm going to give it a little help. No, but I'm hearing all these hypotheses, and that's great. Oh, there we go. Get in there. Go on, get in there. Get in there. Come on, you. Ah! Finally. There we go. He's home. Except now I have a new problem. I can't get him out. Do it again? Burn him again? He's in there. I don't want to do that. Yeah? Shake it. Pop it. I'm not going to pop my friend. Shake it. Break it. Break his home. I see a lot of hands, but mostly it's people I've seen before. So I'm looking. Yes, in the hat. We've been over this. I'm not destroying my friend. Oh, okay. All right.
Get another paper, burn it, and then put it in.
Nope, that won't work. Yes.
Maybe you should break that, and then he might get out.
All these guesses are destructive. Let me see. The reason why Egbert went in there is that something was already in this container when I put him on top. What was in this container? Yeah? What was in? So wait, there's some inside here right now. Fire. There was fire, but before there was fire, there was gas. Very specific. Air, the air that's around us right now. And fire, someone mentioned oxygen. Fire needs several things in order to survive. Hands down. And by the way, if I say hands down, it's not because I don't think you have something incredibly awesome to say. I just want to make sure we can get to all the cool stuff I want to show you. I haven't even blown anyone up yet. We want to be here for that. So, you will. So, fire needs several things to survive, and one of it is oxygen. Just like you, every time you breathe in, that's your body taking in oxygen. When you breathe out, it's mostly carbon dioxide, which we will get to a little later. But when I put Egbert on, hang on, when I put Egbert on here, and the paper was burning, it burned up that oxygen. It's burned up some of the gas, some of the air that was in this container. And that meant there was more air pressure outside the container than inside the container. So it sucked them in. So now all I have to do is make more air pressure inside the container than outside. And in order to do that, I think I might need to get my half-burned paper out of here. And then, let's see, how can I make a little more? Oh, you stinker. Okay. When in doubt, use fire or fire implement. There we go. Okay, let's see. Come on. Come here. Hey, there we go. When I blew in, more air was getting pulled into that flask, and for a brief moment, there was more air pressure inside the flask than outside the flask. And we can talk a little bit more about that, or rather, my assistant, Spectrum Sammy, can tell you a little bit more about air and air pressure and the cool things that we can do with that. So let's give a hand to Spectrum Sammy.
Hi, everybody. How's everyone doing? Good. Did you get entertained by Bionic Bill or Brainstorming Bill? All right. So let's give a hand one more time for Brainstorming Bill before he comes back. And we are going to go over something called the Bernoulli principle. Does anyone know what that is? Raise your hand if you do. What about you? What do you think it is? What? Oh, we're not. Well, it has something to do with burning, yes. Oh. What do you think, buddy? Yes, air pressure. That's a really good guess, and that's a really good answer. So, for air pressure, when the air around us moves faster, the pressure in the air is lower, and then when the air in the air around us is slower, then the pressure in the air gets higher. So I'm going to do an example with this hairdryer and a ping pong ball. So do you mind if?
Yeah, I got it.
Thank you. Does everyone see the ping pong ball?
Yes.
All right. So I'm going to turn this hairdryer all the way up. And okay, one thing, this involves noise, so if any kids are bothered by it, they can cover their ears. There's going to be much louder noises in a minute. Not yet. All right. So everyone sees the hairdryer? Yeah. All right. Ping pong ball. So you see the air would go around the ping pong ball, forcing it to stay in place as it floats. See that? Okay, got it. All right, now let's try something bigger.
Oh,
you guys ready?
I know what. I see it. Okay, this will be loud.
Giant eyeball.
Oh.
It's not real. It's not a real eyeball, guys. It's just marker, but it looks pretty, doesn't it? All right, thank you, Bill. So the ping pong ball, it's a little too small for the leaf blower, isn't it?
Yeah.
It would go right through. So we're going to use this bounce ball. Ready?
Yep. Let's try that one more time.
Try it one more time, guys.
Let's see. Now here's the thing. Let's see how far I can get it to lean before it falls. Does anyone know why it fell?
Why did it fall?
Why did it fall?
Because that.
Yeah, right here.
Oh,
Gravity, yeah. But gravity was there before, but there was also all that, the air wasn't just moving around the ball real fast, holding it in place, it was also pushing it up. So eventually, the air wasn't pushing it up enough to overcome the force of gravity. And suddenly the force of gravity was more powerful than the pressure around it. And that's why it worked. You want to try one other thing with
Yeah,
pressure?
we're gonna do one more experiment with air pressure. So I'm gonna need one volunteer. I'm gonna need someone who listens very well. Let's see, how about you, young lady? Come on. What's your name?
Satoshi.
Sakoshi, I love that name.
Satoshi.
Oh, Satoshi. All right. Are you a young lady or young man? Are you a man? Okay, I'm so sorry. All right, so I'm gonna show you guys with this project. With this bag, we're gonna show the air pressure. So I am going to breathe into this. I'm going to bring this close to my face, and I'm going to breathe into it gently. Close it up. Look at that. That's how much air is captured in here. All right, and now I'm going to have Satoshi. What I want you to do. I want you to breathe in like this. And I'm going to hold it away from you. Okay, ready? 1, 2, 3, go.
Now it just got bigger.
It just got bigger, that's right. So that explains, that's more.
More carbon dioxide.
That is a good guess.
That was
Yes,
easy to do.
it was easy to do. Yes, can we give Satoshi a hand? As everyone noticed, the bag got bigger when Satoshi blew into it. Can anyone explain to me why? In the Minecraft.
Because you were the air is when you were when you were pulling it down, it was making it was like pushing down to make and the end was making it to stop.
That's a good guess. All right, Sonic.
You blowed it into it and then you trapped it.
That's right. We blew it into it, trapped it. But did anyone make an observation about how we blew into it? Let's get someone new. Yeah.
Because when you blew it, it was like the bag away from you. More air got in than just blowing it in.
That's right. More air got in because it was farther away, and when Satoshi blew in faster than me just going. It got more free air. All right, guys. Thank you very much.
Thank you, Sammy. So yeah, when you're blowing into it from further away, it's like the ping pong ball or the other big ball that we were floating before. There's more air pressure, or rather fast-moving air, excuse me. Fast-moving air has lower air pressure than slow-moving air. And by blowing like this, I'm creating a low-pressure area. What happens is all the atmosphere and the air around you wants to squeeze into that spot, and it brings in more air than what was there before. Does anybody remember those, and maybe they still make them, those Dyson fans that don't have blades? Yeah. Have you seen those? Yes, have you seen one? What's in the bag? Not much, a little bit of air. So that's how those Dyson fans work. It's the same principle. It's just creating a low pressure area and putting in and bringing in more air from the surrounding area. So when you do this, you can put a lot more air in the bag than when you smush it up against your face, and you only get that much. It's a pretty big difference. Was that cool? Kind of cool? Would you like to see something cooler? You want to see something cooler? All right. There's a cooler. I didn't say the jokes were good. The science is good. So this, we mentioned a little bit before when we were talking about breathing and talking about carbon dioxide. This is ice. But it's not the kind of ice like you have at home. The kind of ice, and the commentary is unhelpful to the people around you. The ice in there is not made from water. Now, let's say maybe at home you've got one of those nice fancy newfangled refrigerators with an ice machine right in the door. And you get a glass and you walk up and you put the glass into the thing and you're holding it there and it's making all kinds of noise and nothing is coming out. You're like, come on. And then suddenly 18 cubes of ice fall out of the thing all at once. And some of them end up on the floor. And you go, oh, okay. Mom and Dad love it when you do that. Yeah. What happens when Mom or Dad walks into the kitchen after you've done that, wearing only socks, and steps on the floor? What's going to happen to their sock? Yes, and the glasses? Right there. They're going to slip. Why would they slip? What's there? Because there's water there. Ice that we use at home in our kitchen is made of water. This ice is melting, or is it, in my hand right now. My glove isn't getting wet. That is because this is not water ice. This is actually frozen carbon dioxide, the very stuff that you... It is dry ice. Dry ice is frozen carbon dioxide. And dry ice does something pretty cool. It sublimates the same way that that flash paper did. Sublimation means moving directly from a solid to a gas, which is what is happening right now. That's why you see this cloud. And, remember that game we were playing, everybody? Hands up! Hands to your head. One finger in the air. And very good, very good. So this does the same thing as the flash paper. It moves directly from solid to gas. And as you probably remember from my question earlier about dancing and running around outside, gas takes up more space than liquid, and certainly more space than the solid. Whoop, don't pick that up.
That is very cool.
Because
It also is
liquid nitrogen is even colder still. But does anybody know how cold frozen ice is? At what temperature does water freeze? Right there in the middle and back. You, yes, in the yellow shirt.
There's one that just fell.
Is it? Okay, that's all right. That's okay. That's okay, as long as nobody touches it. As long as nobody touches it, because I'm wearing a glove.
It hurts.
But yes, it does. Does anyone know what temperature water freezes? Like, what does it have to be to freeze outside? Yeah. 10 degrees, that's a guess. Okay, yes. 32 degrees Fahrenheit. Fahrenheit, not Celsius, because this is America and we use freedom units. But yes, 32 degrees Fahrenheit is when water freezes. This right here is almost 200 degrees negative Fahrenheit.
What? That's
Way colder than ice. And if I were to touch some of this in about 3 seconds, I would have frostbite and I would have to go to the hospital. So you would have a bad day. Please don't play with this sort of thing. Now, I will tell you that although we usually say don't try this at home, you can definitely do the hairdryer thing at home. If you got a ping pong ball, if you don't own any ping pong balls, ask your parents. They probably have some left over from their college days. That's totally fine. Dry ice, yeah, you can buy it in some places, but please, you must be very careful with it. And if you ever have it, don't keep it in a closed car, yeah. It looks like a volcano. Well, yeah, what's happening here? Does anybody have a guess as to what's happening? Yes, young lady.
So the bottom of that bottle
Uh-huh.
is water, but above the bottle it is white.
Above the water, you see the white gas. You see the white bubbles coming out of there. It's not smoke. It is simply very cold air. It is the carbon dioxide that is coming out of there. Okay. Yes, you can, but not right this second. There's actually going to be a table set up in the back a little bit later with more dry ice stuff, so it's pretty cool. All right. That is better with liquid nitrogen. That is a thing. I don't really play with liquid nitrogen because that stuff, if you think this is cold, that stuff is like you put your finger in there and you don't have a finger anymore. And I want everybody to leave with the same number of fingers and toes and belly buttons and eyebrows that they came in with. But we still actually haven't gotten an answer to the question of what exactly is happening here. Yeah. Yes. That's you.
It's like when you keep the water, it's making bubbles and it's like starting to melt.
Mm-hmm.
And then after how old that, like when you took it out, it showed that it looked like the ice was smoking because it was so cold. And when you kept it inside, then the smoke, then all that smoke would have went to the top, and then it would have started coming out.
Okay. So we got a lot of information. Hands down, thank you. We got a lot of information in there, and yes, so what's happening is, what we talked about is sublimating. It's going straight from solid to gas, and the reason it's happening so much faster in liquid is because liquid is more dense than air. So that means the dry ice is in contact with more water molecules than it ever was with the air molecules, and it's going faster. And because gas takes up more space than water, than liquid, it is expanding, and I don't have, that's okay. I was gonna do one thing, but I'll do another. It's expanding and it takes up more space. Now this is the part where you can taste the science. Do you wanna taste the science?
Yeah.
All right, this is totally safe. What do you think? Yeah.
I remember that kind of taste.
So I'm already hearing people saying it tastes familiar. What do you think? Does it taste like anything?
It tastes like water.
Tastes like water. Okay, that's pretty vague. Is there anything you've ever drank that this reminds you of?
It doesn't. It's cola.
Oh! There you go. No?
Nothing.
Nothing?
It tastes
No?
like cotton candy.
You know? You wanna see? There you go. I heard at least one person say it tasted like soda. Heads your head. Heads your head. Oh, somebody's, there's a lot of slow people. Heads in the air. One finger in the air. And shh. Yes, thank you. So I heard somebody say it tasted a little bit like soda, and that is a great comparison because soda is carbonated. How do we do it? We put carbon dioxide in there, and that is exactly what this gas is. All right. I did suggest that just maybe I might blow you kids up today. So maybe I should. All right. All right. Hang on. This isn't going to happen. This isn't going to happen if everybody's talking. I know it's exciting. Fire is cool. All right. This is called ethanol. Even if you don't know what that is, you've all been somewhere where you've smelled it. A gas station. Most of our gasoline contains about 10% ethanol. It comes from corn. Does anyone here like corn?
Yes.
Lots of people like corn. Why, young men in the space shirt, why do you like corn?
It's corn.
It's corn. Why do you need to eat corn? Why do we need to eat corn? That was a silly question, I know. It's healthy. Why do we need to eat healthy food? Yeah. Okay, healthy food is better, but why do we need to eat food at all? Yes. So you don't starve. That is a complicated but very correct answer. Just leaving aside getting starved, if you don't eat all day, are you going to want to play a lot that evening? No, we're not. What did you say? You wouldn't be able to run around because you wouldn't have enough energy, right? So if we eat corn to give us energy, this is made from corn. Yeah, hands down. and this is made from corn. Let's find out how much energy is in this. Now I'm gonna put a little bit in there. Corn has some carbohydrates, but it's also got protein. It's got lots of things. It's good stuff. All right. Now, quick message for all the dads. Don't try this at home. Don't think, I can get one of those Hinckley Schmidt water bottles and do that. Oh, this is cool. I say this to the dads because I know I am one. I am not needing to say this to the moms. I know because I am married. What I am doing right now, I am spinning this around. Does anyone know why I'm spinning this around? What do you think? So it gets all over the bottle. It's more than that. Ethanol is what we call volatile. That just means it evaporates very easily. And a lot of it is actually evaporating in here right now. So I'm going to open this up and just make sure I don't have anything extra. Just a few drops. All right. Okay. Now, this particular experiment is called swish, whoosh, ah. We did the swish. The next thing you're going to hear is a whoosh. It is a little noisy. It's not a big bang. But if you are sensitive to whooshy noises, might want to cover your ears, but I'll warn you, okay? So don't worry, I'll warn you. And then you're going to go, ah. All right. By the way, I can only do this once. So make sure you are looking. Okay. I think let's see. I want to do this on the floor. Can everybody see if I'm like this? All the kids can see if I'm sitting like this? Okay. Stay behind that line. Can I get a countdown? 5?
4, 3, 2, 1.
Look at that. Look at that. Look. Yeah. Okay, yeah, I knew there was going to be it again. Now, it's not safe to do it again because there's still going to be a little left in there. In fact, I might even get, oh, there it is. Whoa. Woo. See, that's why we don't want to try that again. Not until this has had time to come out. Okay, on your seat. Go on. All right, now there was one point I want to make about what you saw there. Was it a single whoosh, or did it go a little bit differently than that? Yeah, a little differently, yes. Well, sorry?
I've actually noticed.
I didn't hear you, miss.
It didn't went swoosh.
It went swoosh, okay. Did anybody notice, yeah?
The entire bottle flamed up because the ethanol was all around the sides of the bottle, and ethanol was flammable.
Children, I don't think you can hear him. Okay.
Ethanol was around all the sides of the bottle, and ethanol was flammable.
Yeah.
So the flame spread across the whole bottle.
Yeah.
And it contained a lot of energy, so
It swooshed out. That is a wonderful observation, very good description of what happened. But, hi, how you doing? Do you want to hold the bomb? No. But if you were looking really closely, you might have seen that the fire kind of went whoosh, and then it died down, and then it was like a little whoosh, and another little whoosh, and another little whoosh, and then it stopped. Almost as if it was breathing, because it was. Fire is like you and me. It needs to breathe. And the initial whoosh shoved all of the oxygen that was available. Either it burned or it was shoved out of the bottle. More oxygen came in because there was less air pressure, new oxygen, more fire. Oh. So, I want to thank all you guys. You've been great. I really appreciate it. Before we go to our other activities, I want to see if everybody can take the Mad Science Pledge with me. Can everybody stand up? All right. Put your hand over your heart. Repeat after me. I promise to stay curious, ask questions, and find the answers. Now give me your best mad scientist laugh. Thank you guys. Give yourselves a hand.